Greetings and welcome, friends. Yesterday you talked about the law of sines and its ability to solve certain non-right triangles. Today we're going to determine that it actually has, well, first of all, there are some cases that it just flat out can't solve, and then there's other cases where we're unsure of which solution is right. And that's referred to as the ambiguous case of the law of sines, or as I like to think about this as Harry Potter in the ambiguous case of the law of sines. I imagine if I titled my YouTube video that, I'd get far more hits. Haha, classic. So, let's talk about why this case exists. Now let me flash back, let me do a little recall here. Back to our days of geometry and proving triangles congruent. And back in the day, you had a series of postulates like, for instance, there was the side, triangle congruence postulate that said if I could prove that these three corresponding sides match up with these three corresponding sides, then I know that these two triangles are congruent, right? So that looked something like this, where you could have like and and if I prove this is congruent to that, and this is congruent to that, and this is congruent to that, these three triangles are the same triangle, right? There's a flip-flop there. Well, there's two triangles, but they are congruent to one another, right? So that was a thing that happened back in the day. We also had side, angle, side, where if you had two sides and their included angle, that if you had that as your starting information, that there is only one way to draw that other third side, meaning there was only one possible triangle for those to be arranged. Like they couldn't be arranged any different way. These triangles must have been congruent. Let's see. What was the one you were just suggesting? Did you? AAS? That's your last name. That's right. Perfect. So angle side would be two angles and their non-included side. All right. So the order of the letters actually is significant. So if I have an angle, an unknown length, an angle, and a side length, it turned out there was kind of only one possibility for the other dimensions to land. And we were able to prove congruence, right? So if, however I'd set this up, right, if I had those same two starting angles and I said you're going out 20 paces this way, there was only one way, one triangle that would exist for those two, and you'd have the same triangle every time. All right, so angle, angle, side. We also had angle, side, angle. ASA, right? Which I think you guys can tell, right? The two angles and their included side, just like this was two sides and their included angle. So this would be like this. So imagine I've got a set side length and set angles. There's only one location that these two parts could line up. Even though I don't know the lengths of these, or it wasn't given to me, it's going to happen every time. So if I have a set angle, a set length, and another angle, right, these are going to intersect at the same place every time. These two triangles would be congruent. And then, much to the disappointment of the humor of middle schoolers and young people everywhere, there was no such thing as a $. All right, this was like an illegality in the realm of mathematics. All right, and part of that is what we're going to expose and talk about today. It turns out I can't prove those two triangles are congruent, but I can prove that they are of one of two cases. All right, it's like the ambiguous case of the law of sines. It's like we're at a murder mystery and we found the DNA and the fingerprints, but then we found out that our suspect is a twin. And we're like, oh man, I know it was one of them, but I don't know which. And that's the problem we have today, right? So there's no ASS in math, right? Mathematicians are very appropriate with their language. So the idea was if I have a side, all right, so I could have, right, a side, and a starting angle, right? Say I have this for a starting angle. And then the side opposite that angle, say I had this dimension here, right here, right? Now, the issue was that I couldn't guarantee that this dimension was going to land in the right spot. It also could actually land over here, is the issue. Oh, wait. No. I just did this wrong. Yeah. It would be swinging the other way. All right. So imagine like this on a hinge, because this angle is undefined to us. So this could swing the other way, and it could also have landed here or here. So there's two possible locations for this. So it could have been this version, right? Whereas the other option for intersection was there. So I actually have these two possible cases that I had to consider. I knew it was one of them. Back at the time, we just said you couldn't prove the triangle's congruent, but maybe mathematicians didn't let on to you. Your geometry teacher didn't let you know how close you were. Like where you kind of had, I don't know if I'd say a 50-50 chance, but there was only two possible outcomes for it. Now it turns out in the world of right triangles, there was an ASS. Except it wasn't called that, it was called the Hypotenuse Leg Theorem. And we were certain in the world of right triangles. All right, so if I have a right angle, all right, and a side and another side, it actually turned out that this could only land in a set position, angle, side, side, hypotenuse and a leg sort of thing is kind of what was going on there. So it turns out there was only one possible outcome for that. Part of it is, well, if you think about it, the right triangle, since it's right, if I have two sides, I can automatically find the third using Pythagorean theorem. And then by side, 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 I've proven the triangles are congruent. So, so hypotenuse leg, if I have the hypotenuse, the leg in a right triangle, right, hypoteni, if that's plural for hypotenuses, are only existent within right triangles. So I just want to point out that hypotenuse leg existed. But this, well actually, whoa, settle down there, computer. These are the two situations that we're going to be referring to today in the case of the ambiguous case of the law of sines. All right, so that's what we're going to be talking about. So I've kind of demonstrated this idea of this like hinge on this point a little bit, but I want to actually get a little bit clearer with that. I've got Geometer Sketchpad here, and here is an acute angle. All right, so it's actually going to be a slightly different rule set for acute and or obtuse. And so here I've got my angle is fixed, I've got an adjacent length is fixed, and my opposite length is fixed. And I can swing this around, all right? So here you can see this is too short and it's not reaching the other side. Actually, this is a classic example. And the relationship is if this opposite side is shorter than the height, all right, drop down from there, it won't reach the other side, right? I think you guys could see that. It's like, my kinesthetic learning demonstration would look like this. Let's see, just a second, I gotta scoot over. That window's got too much contrast back there. So imagine like here's one side, and here's my side and my angle. Let's see, there we go. And imagine I'm like, I can't reach. Right? That's kind of what's happening in that situation. If my opposite side is shorter than the height from here to that arm, right? I can't do it. It's impossible. And that's the situation that I'm describing right here. Let's see. So where are we here? So yeah, that's fine. That's fine. So if it's too short, no triangle exists. Okay? So it's actually, that's what's really sneaky. Maybe no murder happened at all, and it was just the guy choked while eating a shrimp, right? Like, that's kind of the possibility. So some of the problems that you'll have tonight will be tricky in that way. It's like, there's no triangle formed with the dimensions you just gave me. Please, right? And then there's the case of what happens if this is exactly the length of the height? Well, if that's true, then there's only one triangle that would exist, right? And that would be a right triangle. If it's exactly the length of the height, then this would have to be a 90-degree angle. And that's kind of our hypotenuse leg situation that's arising, okay? And then what do you think is going to happen if it's longer than the height? Look at this. Well, if it's longer than the height, imagine this swinging back and forth, right? and it could land over here and be this large and acute triangle overall, or it could swing over here and be this small but obtuse angle, right, and obtuse triangle here. So there's actually two cases that can occur as a result. All right. So let's talk about the ambiguous case of the law of sines with acute angles. So I'll call this case 1 if your angle, I'll just call it A, is less than 90 degrees. All right, and that looks like this, roughly. All right, and I use angle, adjacent, and opposite as my language just to try to make things make more sense. But the idea is, even though I know these dimensions, it could swing and land in either of those locations. Now, the fact that I know these dimensions, and these are congruent, I actually have the base angles theorem and its converse regarding isosceles triangles. That if I have two congruent sides in a triangle, then the angles opposite them are also congruent. So even though this angle here is not part of either of my triangle solutions, it's helpful for me in realizing that this angle is going to be supplementary with it. Right, this angle and that one add up to 180 degrees. That will come in handy later on. So this two triangles case, or possibility, occurs specifically when my opposite is bigger than my height. All right? And in describing my height, I'm actually going to give you an equation for this. This height is going to be, in a sense, the value of, let's see, what did I call this? Well, your book calls it B sine alpha. I'm going to refer to this as angle, and this is adjacent. This height, I'll just say the height is equal to the adjacent, because I don't want to use B sine alpha because maybe our variable angle inside names aren't always going to be the right letters. It'll be adjacent times the sine of our angle. Okay? And that's going to be the formula for our height in all of these situations where an angle side-side situation occurs for us. Okay? So the reason that this is true, well, if you think about it, you don't have to draw this, but if this is I could kind of view this as like a right triangle here. And from my angles perspective, this is the opposite, and this is the hypotenuse. So I would say sine is equal to little h over the adjacent, and then height, I would just multiply both sides by the adjacent. So that's kind of where this formula comes from. So it's not just like willy-nilly, it happens to be the same every time. Because specifically these cases are referring to our angle side situation, right, that I'm referring to, dollar sign there. So if the opposite is bigger than the height, then there are two possible triangles. All right? Let's grab a snapshot of the other one. So if it's equal to the height, let's see, I don't think it'll actually let me snap it to the right spot. So I'll just draw it like this. So there is one triangle, and in fact, I happen to know that it's a right triangle. And this occurs anytime the opposite is equal to the height. So if your opposite is equal to the adjacent times the sine of alpha, all right? Then I know there's only one triangle and there's no ambiguity whatsoever, right? That's hypotenuse leg. And then the other situation was it's too short and we had no triangle formed. And that occurs anytime the opposite is less than the height. And that, of course, is when I'm like, and I can't like make my hand reach my other elbow, right? That classic situation. So those are the three possibilities that we need to know about. So some of our problems tonight are specifically just going to be saying, figure out for us how many possible triangles there are. And it's not actually asking you to find the triangles, it's just saying how many are there. So let's actually do an example of that right now. I think I can fit it down here. So let's say we want to determine the number of triangles. Determine the number of triangles. So let's say I have angle A is equal to 30 degrees as part of my given information. Little a is equal to 3, and little b is equal to 10. So I like to draw this picture kind of exactly as I have in these diagrams every time. Because, right, unless they give us a picture, I've got the choice to draw it how I want. All right, so here's my A. My B is going to be down here because I know little b this time, right? So B is my adjacent, and then my opposite is the 3. And the question is the 3 going to be long enough to hit once, hit twice, or maybe it's too short and it can't reach at all because it's doing the swing back and forth sort of thing. So, so this is kind of my situation here. I'll describe it kind of like that, right? And then obviously angle C is up here. So this is a 30-degree angle. This is 3, and this is 10. All right, so in order for me to determine this, I have to know what is my height. And to calculate height, as I said, it's the adjacent times the sine of the opposite. Okay, so for us, sine of the angle. What am I saying, friends? Guys, please. Angle. So for us, h is equal to the adjacent, so that's the 10, times the sine of 30. What is sine of 30? You guys got that memorized? 1/2, right? Square root of 1 over 2, which is 1 over 2 or 1/2. So that's 10 times 1/2, which is 5. So, looking at this, what situation do you think we're in? I just found out that h is equal to 5. There's no triangle, and why? Since 3 is less than 5. All right, my opposite is shorter than the height, and it's one of these situations right here. Okay, so that's how you would do that analysis. All right, so that's not that bad. Let's consider case number 2. In which angle A is greater than or equal to 90 degrees. And I believe I've conveniently got another sketch. So if my angle, actually, let's see, do I remember the rule for this? What was it, command? Oh, bam, look at that. I even knew the shortcut to make these larger. How great is that? So looking at this sketch, all right, if I have an obtuse angle, notice no triangle is formed anytime my opposite side is shorter than what? The adjacent, right? If it's shorter than the adjacent, it's not even reaching back. Like it can't count. Like I just said, like, all right, head out into space in this direction, and I didn't give you enough fuel for the return trip. Like you can't get back, right? And never mind back to the first point. Like you have to get back to a point way over here, right, to make an actual triangle. All right, so if it's less than the adjacent, no triangle is going to exist. And if it's greater than the adjacent, it looks like I have an obtuse triangle being formed here. Now, in this case, even if I swing it around, all right, and maybe the sketch doesn't show this well. Even if I swing it around, I just want to point out this is no longer an obtuse triangle based off of having this first angle here. All right, so the comparison is only between the opposite and the adjacent this time. So let me grab a snapshot of this. Nope. There's my snapshot. Click, click. So if my starting angle is obtuse, I actually don't even care about the height this time. I just figured I'd show you where it is. I have one triangle anytime the opposite is greater than the adjacent. And then the other situation was, let's see, no triangle occurs anytime the opposite is less than the adjacent. Actually, I might even say less than or equal to the adjacent. Because what happens when it's equal to the adjacent? Yeah, it doesn't actually form a triangle. It's like it's so close, but I have an angle, but it wasn't enough to actually form a third edge. All right, so that's the idea there, right? Less, it's no triangle. More, it's enough to swing around and land right in the right spot. Whoa, I just broke that crazy. Anyways, so those are those two situations. So let's consider one of those possibilities. Yep, no problem. So let's consider that. And let's do an example. All right, find all solutions for each triangle. Okay, so if I only have one solution, then I'm going to find all the angles and the sides. If I have two solutions, I need two sets of angles and sides. If I have no solution, then I'm done, and that's a good deal. So let's say my starting information is side A is 4, side B is 3, angle A is 112 degrees. So looking at this situation, am I in case 1 or case 2? Case 2, because my angle is obtuse. All right, so I've got a triangle, 112 degrees, I don't know, something like this. The adjacent is going to be not the same letter, and then A is 4. And actually, I can already see that this is going to work out. So I'm going to have, I guess I'll label this, so this would be A. If this is side B, then angle B must be over here, right? And then I'll just call this angle C. And so I've got a 112 degree angle. My side B was 3, and my side A, the opposite, was 4, right? So how many triangles exist, and how do you know? Because 4 is greater than 3, right? The opposite is greater than the adjacent. So we are in this situation here, right? So now all I have to do is just use plain old law of sines to figure out the rest of this, which you guys are probably pretty good at right now. So what should I find first? What's the next stepping stone? Well, I can't find angle C because I'd need side C to pair with that. So I actually have to find angle B. And I can't find side C because I can't use Pythagorean theorem since this isn't a right triangle. So yeah, so angle B is the next step by default. So I would say sine of B over, let's see, 3 is equal to sine of 112, which I know is positive because sine is positive in the second quadrant, of 4. And then I'd multiply both sides by 3. And I'd get sine of B is equal to 3/4 times the sine of 112. And how do you get B by itself? Sine inverse. So I'd get angle B is equal to sine inverse of 3/4 times sine of 112, double close parentheses. So angle B is 44.06 degrees. Not too shabby. And now that I know B, now I can find angle C, right? And that's just going to be 180 minus A plus B. So that's just going to be 180 minus parentheses, second answer, plus 112 close parentheses. And I get 23.94 degrees for angle C. And now I could find side C because I have an angle to pair it up with, right? And side C, I'll be able to do that. And I'll probably relate those still back to the A's. And in this case, since I'm looking for a side and not an angle, I'm going to use the reciprocal version of this law of sines. I like to have my thing I'm looking for always on top. So this will be little c over sine of 23.94 equals, technically degrees. Technically it's inaccurate if I don't label it degrees because there will be another angle measurement that we'll talk about next chapter that doesn't have a label. So figured I'd point that out. But not that I'm going to necessarily play hardball with you on that, but be aware of it. Equals, let's compare it to the A's, 4 over sine of 112 degrees. So little c is equal to 4 times the sine of 23.94, because I'd multiply both sides by sine 23 over sine of 112 degrees, right? Because to get c by itself here, you'd have to multiply both sides by its sine 23. I think you guys agree. So c is going to be about sine of 4 times sine of my second answer. Conveniently, it's the last thing in my calculator. Divided by sine of 112, close parentheses, and I get 1.75. So in this case, this ended up just being like a plain old law of sines problem in the end. It just required this additional analysis. Now, tonight and today, we're only going to have problems that have as many as one triangle, as far as ones I actually have you find all solutions for. All right, tomorrow we'll talk about the 2 triangle cases specifically and how to solve those. It's related to, let's see, the only 2 triangle situation is this one. And it requires a little bit of these relationships between these angles to be able to figure it out. But it's not that bad. So anyways, thanks for watching, internet friends, and have a great day. Bye-bye.